Hello everyone, welcome back to lecture video 3. This is our last lecture video for this topic, chapter 15, Reactivity Series of Metals. It has been a really content-heavy ride in lecture videos 1 and 2, but I would need you to actually learn lecture videos 1 and 2 well before coming on to lecture video 3. Now this video probably will be the shortest of the 3 videos because you have learned the bulk of the chapter already. The bulk of the chapter meaning the reactivity series itself and displacement reactions. Displacement reactions are really important for us to understand, and you must ensure you understand displacement reactions before embarking on today's video. If you have not really understood displacement reactions, please go back to lecture video 2. If you still don't understand, please message me to let me know anytime, and I'll be glad to explain it to you once more. But today, we are actually going to go on a whirlwind tour of the rest of this set of notes. Now, the rest of this chapter is quite easy, so let's make a start. Now, we are now on page 17 of the notes. And this is where we learn about the thermal stability of metal carbonate. When we say thermal stability, we mean how stable is it to heat? Will it decompose? Obviously, if it's stable, it doesn't decompose. However, if the metal carbonate is unstable, it will decompose. All right, so the idea here is decomposition. Will it or will it not? Okay, so again, we return back to how do you think reactivity would affect whether the metal forms a stable carbonate or not? What does it mean to be reactive? For instance, potassium is really reactive. It explodes. Boom! So when potassium explodes, it forms K plus ions. K plus ion would form strong electrostatic forces of attraction with other N ions. For example, if K plus and CO3 2 minus attract each other, they are happy together. K plus does not want to go back to being K because K plus is great, K is not. Potassium atom is unstable. Potassium atom is reactive. It will boom and form K plus. Once K plus forms, it doesn't want to look back. Similarly, sodium. Sodium 281, not stable. Outermost shell is not fully filled. So the sodium atom will lose one valence electron. Boom! It loses one valence electron, it forms Na plus. The moment Na plus forms an ionic compound, it doesn't want to go back to Na. And that's the idea. So it tells you more reactive metals like potassium and sodium, once they react, they boom and form a compound. The compounds generally don't decompose. More reactive metals, boom, explode, react. After they react, they form more stable compounds. And once the compounds are formed, they don't decompose. They are more difficult to be decomposed by heat. And this is particularly true for potassium and sodium. Potassium and sodium compounds do not generally decompose. So you can heat them up to 800, 1000 degrees Celsius, but they will not decompose. All right. How about other metals like calcium, magnesium? So calcium and magnesium are less reactive than potassium and sodium because they are lower than potassium and sodium in the reactivity series. But they are still quite reactive, right? So even though calcium and magnesium carbonate could decompose, it's gonna require a higher temperature for that to happen. Okay, so the idea here is more reactive metals, more difficult to decompose. They may need a higher temperature before they start decomposing. All right, so shown here, I've given copper 2 carbonate. Copper 2 carbonate is a very typical carbonate which you can decompose in the lab. This is because copper itself is not a very reactive metal. Copper is quite low down in the reactivity series. So copper 2 carbonate should be quite easy to decompose. And indeed, when we decompose copper 2 carbonate, it forms copper 2 oxide and carbon dioxide gas. So the CO3 basically decomposes to form CO2 and of course the oxide O with the copper. Okay? So that is the reaction. CuCO3 decomposes when heated to form CuO and CO2. All right. Now, if I wanted to see the extent of how much carbonate has already decomposed, what can I measure? Okay. Well, the obvious thing to measure would be, okay, I already know the carbonate decomposes to form CO2 gas. CO2 gas is a gas, right? I could measure the volume of CO2 gas formed. And how would you measure volume of carbon dioxide gas? Using a gas syringe. So this is what we learned in chapter 1, right? Selecting the right apparatus. So to measure the volume of carbon dioxide gas, we can actually use a gas syringe. Now, what can we tell from this? Obviously, more CO2 formed, greater extent of decomposition, right? If there is a greater extent of decomposition which has happened, you should get more CO2 formed, a greater volume of CO2 formed. Now, this is one variable that can be easily measured in the lab to see how much or to what extent has the carbonate decomposed. Another variable that could be measured is the mass of the solid. If we look at the state symbols, the solid at the start was the carbonate, at the end it was the oxide. The mass of the solid decreases. You can see that clearly. The mass of the solid should decrease. Why? At the start, the solid is CuCO3. At the end, it's just CuO because CO2 forms a gas and evaporates, escapes away. That's why the mass of the solid decreases. So, if there is a greater decrease in the mass of the solid, again, we can deduce there is a greater extent of decomposition that has happened. Because if the solid's mass goes down, that means it's decomposing. If it goes down more, that means it has decomposed more. Okay? Now, this is very important because now knowing the variables that can be measured, I can actually perform experiments. I can either measure volume of CO2 gas or I can measure the mass decrease of the solid. And from that, we can work out which carbonates decompose more easily. So, very important, sodium and potassium, the top two, potassium carbonate, sodium carbonate, they are stable to heat. They are unaffected by heat. Unaffected by heat means what? No CO2, no decrease in mass. Very important. All right. So potassium and sodium carbonates do not decompose. They do not form CO2 when heated. They do not decrease in mass. Unaffected. No change. Now we move on to those below them. Calcium carbonate, magnesium carbonate, and so on and so forth. These can decompose. And when they do decompose, they decompose to form the oxide. So zinc carbonate decomposes to form zinc oxide and carbon dioxide. So they do produce CO2 and they do decrease in mass. But is there going to be a difference? There is. Calcium needs the highest temperature to decompose because calcium is the most reactive of this list. So even though calcium carbonate is able to decompose, it needs the highest temperature to do so. Copper 2 carbonate, on the other hand, requires the lowest temperature to decompose. Copper 2 carbonate is very easy to decompose. You just need to heat it to beyond 200 degrees. That's easy to do with a Bunsen burner. Okay, so why does copper 2 carbonate need the lowest temperature? Because copper is the least reactive of this list of metals. Now, silver carbonate is even more interesting. Silver carbonate decomposes directly to form silver metal. And this is because silver oxide produced is unstable. So the silver oxide itself decomposes to form silver. All right. So I think this is not a very difficult concept. What you must remember is how dramatic I was at the start when I told you potassium, potassium, boom. After potassium forms K plus and a compound, it's not gonna go back. It's not gonna decompose. It just wants to be in a compound. Leave potassium alone. Same with sodium. Boom. Forms Na plus, forms the compound. Once sodium is in a compound, it's not going back. It wants to be left alone. Leave sodium alone. All right? Can? Then we come to the list in the middle. So you need to know the more reactive carbonates will need a higher temperature to decompose because they are more stable. All right? So now if I were to plot a simple graph of mass against time. First, we have our sodium and potassium. Sodium and potassium carbonate will not change in mass. It remains the same mass, no decrease. Then we come to the calcium, copper. Calcium, copper. All right. So the decrease in mass will actually be more significant for copper to carbonate at the same temperature. Okay, I'm of course measuring at the same decomposition temperature. So for the same temperature, copper to carbonate should decrease in mass more because it decomposes to a greater extent. All right, Ken? So with that, we conclude all the reactions of metals, from displacements, from acid plus metal, from metal plus water, metal plus steam. We have finally finished the reactions of metals. Now, for the interesting bits which are left, let's move on. So a lot of us have talked about K-pop, cultural heritage. It's undeniable that Korean culture has infiltrated, okay, every single aspect of modern life. Pop culture today is unimaginable without mentioning Korean dramas, Korean songs. But South Korea as a country did not used to be rich. Okay, they did not used to have such a vibrant arts and entertainment sector. To support this kind of art sector, you definitely need to have certain economic foundation. So how did South Korea become rich? So for those taking history, you may have heard the Korean peninsula was divided into North and South Korea in 1950. Okay, and then the Korean War broke out. After the Korean War ended in 1953, the North and the South are still divided till this day. Now, what's interesting is that South Korea, when it was started off in 1953, had zero factories. They had no industries to speak of. South Korea was actually an agricultural society which was focused on farming. Okay? So, how then did South Korea become so rich? Are they all doing farming and agriculture? Of course not. When you think of South Korea today, you think of K-pop. But besides that, you also think of Samsung, LG. These are big brands. In particular, Samsung. When you hear of Samsung, you think of phones, refrigerators, electrical appliances. Clearly, there must be a lot of research going on in electronics. And for that, you need metal. Where does this metal come from? So South Korea actually became rich in the 1970s alongside Singapore. All right, Singapore and South Korea, one of the few Asian countries that experienced this economic boom in the 1970s. And the reason why South Korea took off in terms of economics is because of the iron industry. South Korea realized that they could extract iron metal from the rocks that contain iron. And by doing so, they can produce their own iron. Now, how is iron useful? So we have said this in lecture video 1. If there is iron, you can make steel. If you can make steel, you can do construction, you can build ships, you can build weapons. And because of that, the steel and iron industry propelled South Korea to its current wealth today. which of course lays the foundation for Korean dramas and K-pop. If you watch Korean dramas, very often you hear this word chaebol. Chaebol literally means a big Korean conglomerate company. So like Samsung, LG, these are examples of chaebols in South Korean society. All right, so you always have a handsome male lead from a very rich family which runs a huge company, and that whole idea actually came about when South Korea decided to start the domestic iron industry. And many of these big companies that we know of today, they actually started off making iron. So how is iron made? How do we get metals from the rock? So let's find out. Now, obviously, metals don't exist as metals in the soil. If you walk around, you see rocks, you see sand. You don't see glittering, shiny metals, right? If you walk along the street. Why is that so? You don't see shiny metals as they are because the metal has reacted with oxygen, right? So, for instance, iron metal doesn't exist as the metal on its own. Iron would have reacted with oxygen to form iron oxide, which clearly is not going to be shiny, gray, silvery. Okay, so very often they have combined with oxygen to form oxides. And these oxides are ionic compounds. Very important, they are ionic compounds. So these ionic compounds are now found in the rocks. So for example, iron forms Fe2O3. It's in the rock. Now the rock is called hematite. All right. So the rocks that contain metals are called ores. So the ore of iron is called hematite. Hematite contains iron oxide. Okay, so why so confusing? Why not just straight away say iron oxide? Now, the rock hematite is mostly iron 3 oxide, Fe2O3. But of course, being rocks, you also have other impurities like sand, right? It's inevitable that your rock, your ore contains some sand as well. Okay? Now, interestingly, for example, zinc actually reacts with oxygen and also carbon dioxide to form zinc carbonate, and that is in calamine. Calamine is another rock mineral. Okay, it's an ore of zinc that contains zinc in the form of zinc carbonate, sorry. So you can clearly see, right, all these metals, they are not going to exist on its own. It's a compound, it's an ionic compound. So you need to find a way to somehow separate the compound, break down the compound to get back the metal. And this is what we're going to look at today. So, how do we do this? Again, reactivity series. We come back to the reactivity series. So, the idea is last lesson, we actually spoke about reactivity series. This lesson, we started off talking about decomposition of compounds, right? So, potassium and sodium, once they react to form the compound, it doesn't want to go back. It doesn't want to come back again. Once potassium forms K plus, it wants to stay as K plus. This means that if you wanted K plus to go back to become the metal, to be extracted, it needs a lot of energy. K plus doesn't want to go back to K. It needs a lot of energy to do that. And that energy needs to come in the form of electricity. So actually, metals above carbon need to be extracted using electricity, and this is called electrolysis. We need to use electricity to break down the compound. So this word electrolysis has two parts to it. Electro means electricity. Lysis means break down. Okay, so I'm using an electric current, passing an electric current through the compound to break it down. And this, you can imagine, is a huge investment of energy. And this is testament to the fact that the most reactive metals actually form very stable compounds that cannot be decomposed so easily. So for instance, sodium metal is only obtained by electrolyzing sodium chloride. You need to pass electricity through sodium chloride in order to break it back down into sodium metal. That is how reactive sodium is. Once sodium forms sodium chloride, it just doesn't want to go back. Once it forms Na plus, it doesn't want to go back. It rather be left alone. Okay? Now, For the metals that are below carbon, there's a very useful reaction you could do. Last lesson, we have learned this, right? So for instance, copper 2 oxide with carbon. Because copper is below carbon, copper can be reduced by carbon. So CuO is reduced to Cu by carbon. And this works because copper is below carbon. Now in the process, the carbon is oxidized to carbon dioxide. Okay, so below carbon, we actually just reduce the oxide with carbon. This is the most common method to actually extract the metal. Don't you realize at the end of this reaction, we get the metal? And this reaction is still used to this day. This is by far the most important chemical reaction that powers our modern life. Without this chemical reaction called reduction of oxide with carbon, we just can't extract metals. If you can't extract metals, you can't make any appliances at home that you have today. Okay, so metals below carbon are all extracted by reducing their oxides or their ores with carbon. Okay, so we have done above carbon cannot reduce with carbon. Above carbon need to use electrolysis. Below carbon, if the metal you want to extract is below carbon, then you can just reduce their oxide with carbon. Okay, so good example, potassium and sodium must be electrolysis. Calcium, magnesium, also electrolysis. Aluminium, also electrolysis. Why? Because they are above carbon, so they cannot be reduced by carbon. Okay, they will require the most energy to extract because these are the most reactive metals. Metals below carbon can be extracted by reducing their oxides with carbon. Okay, now finally, we have one last member of the reactivity series right at the bottom, gold. Gold is right at the bottom of the reactivity series. This means that gold is the least reactive metal of them all. Gold is so unreactive that it literally doesn't even react with oxygen in the air. So gold is unreactive, it doesn't even react with oxygen. If it doesn't react with oxygen, it doesn't form oxides. And therefore, gold actually is the only metal that's uncombined. All right, gold is found as the uncombined metal in the ground. Another way to say uncombined is called native elements. These are the same thing. So native element just means that the element has not reacted with other things, it's just on its own. Okay, so now if you zoom out, you can see A, B, C. May I encourage us to learn these three separately, but with reference to their position in the reactivity series. So A, above carbon, cannot be reduced by carbon, therefore must be extracted by electrolysis with a lot of energy. B, below carbon, can be reduced with carbon, so we heat up the oxides of these metals below carbon with carbon. So like zinc oxide plus carbon, iron oxide plus carbon, copper oxide plus carbon. All right. Finally, C is just gold. Gold is so unreactive, it doesn't form any compounds with oxygen normally. Therefore, gold exists as the native element or the uncombined metal in the ground. Now, I've given you another example of an equation. Okay, so zinc is below carbon. Zinc is below carbon in the reactivity series. Therefore, zinc oxide can be reduced by carbon and you form zinc metal. Great, I get zinc metal and carbon dioxide gas. Okay, now if you have forgotten this reaction called reducing metal oxides with carbon, please go back to lecture video 2 to revise. Now let's move on. Now, this is our last part already of extracting metals. It's a little bit of history again. So I've given you different metals and the time that they were first discovered. How many years ago were they first discovered? And their abundance in the soil on Earth. So you notice that some metals were discovered a really long time ago. Some metals were discovered really recently. So, do you think there is a relationship between when it was first discovered and the metal's reactivity? Let's just look at these examples. Calcium, 206 years ago. Sounds long time ago, but when you compare calcium with gold, the comparison is so stark. Gold was discovered 8,000 years ago. So what do you notice? Gold is a less reactive metal for sure, right? Gold is at the bottom of the reactivity series. So less reactive metals like gold and also lead probably were discovered a longer time ago. You're talking about a few thousands of years ago. So gold and lead, they were discovered thousands of years ago. Copper as well. Okay. And that's why you had a Bronze Age. Bronze was basically copper and tin. All right. Now, more reactive metals, obviously, like calcium and sodium, were discovered more recently. So to you, 200 years ago is quite old, but it's not. Okay, 200 years ago in science is considered quite recent. All right. Now let's try to use some understanding to explain why more reactive metals like calcium and sodium were discovered more recently. So what did we just learn about more reactive metals? So these metals like calcium and sodium, they are above carbon in the reactivity series. So sodium, calcium, they are above carbon. And because they are above carbon in the reactivity series, they cannot be reduced by carbon, right? We just learned that. So like calcium oxide cannot be reduced by carbon. Sodium oxide cannot be reduced by carbon because it's above carbon in the reactivity series. So this means that they form very stable compounds and must be extracted by electrolysis. So to extract calcium metal, we actually need to electrolyze, pass electricity through calcium chloride, for example. Okay? Okay, so now I would like for you to take this down. It's a little bit of history, a little bit of trivia, but I think it's worth for us to know as well. Now, if you look at gold, gold was discovered a long time ago. Okay, gold has always been a very valuable metal, and it's been known to many generations of people. You might be wondering, so gold was discovered a long time ago. Gold is unreactive; it's an uncombined element. So why should gold be expensive? I mean, if sodium is expensive, you can understand why. Because sodium is difficult to extract. You need to use electrolysis for sodium. So I can understand why sodium is so expensive. But why is gold so expensive? Surely it has not to do with the reactivity, right? Gold is unreactive, it's easy to extract. Now, gold is expensive not because it's difficult to extract. Gold is expensive because gold is very rare. There is so little gold on Earth. You can clearly see the number for the abundance is so low. This tells you that gold is very rare. So it is very expensive. The cost comes from the rarity, not from the difficulty of extraction. Okay? And with this, we have actually finished the extraction of metals. So again, may I please encourage us to revise the reactivity series and how it impacts extraction of metal. In particular, you need to revise the previous page, page 20. Learn the ABC well. All right, I've segmented page 20, the reactivity series, into A, B, C for this reason. Please learn it well. All right, and that concludes extraction of metal. Now, let's move on to the very last part of this chapter, which is rusting. Now, rusting is something that's really, really straightforward. So let's just go to page 23. Now, I'm sure you are familiar with rusting. Okay, you have seen your tables and chairs rust before. In particular, if you scratch the black color paint off the tables, legs, and chair legs, you will see that it will start to rust over time. So the reason why it rusts is because the iron metal used to make the legs of the table can react with oxygen in the air and water to form rust. So what is rust? Rust is hydrated iron 3 oxide. This is Fe2O3 dot XH2O. So if you recall, the dot tells you this is water of crystallization. The reason why it's X is because it's a variable number of water of crystallization. That means it can be a different number of water of crystallization depending on how humid the air is. Now, the water of crystallization tells you this is hydrated. Okay, so what is the opposite of hydrated? The opposite of hydrated is anhydrous. Anhydrous means dry. Okay, now shown there is the equation for rusting. Don't worry about the equation. Okay, don't worry about the equation, all right? I'm just demonstrating to you. Now, so what are the conditions needed for rusting? There are two conditions I can imagine. You know, the first condition is the presence of oxygen in the air. There obviously must be oxygen. The second thing that must be present as well is water. Now, the water here need not be liquid water. The water here could actually just be water vapor in the air. So for example, in Singapore, Singapore's air is really humid. Humid air means it has a lot of water vapor. So the water vapor in the air is sufficient as well to cause rusting to occur. Okay, now rusting is also a redox reaction. I'm sure you can see that. So may I encourage us to think through in terms of oxidation states why rusting is a redox reaction. I would like to encourage us to look at this equation and perhaps spend some time to think through what's oxidized, what's reduced. Okay, so now let's move on. Now, you can actually conduct different experiments to investigate what conditions are necessary for rusting. How do you prove that water is needed for rusting? Well, one way to prove that water is needed for rusting is to basically set something up and remove the water. Get rid of the water and see if the iron will still rust. Similarly, how do you prove that oxygen is needed for rusting? Set something up, remove the oxygen from the setup, and see whether the iron will still rust. So the idea is removing each condition, and then you see whether the iron rusts. How do you remove it though? Now, how would you remove oxygen? To remove oxygen, first, we must boil the water. Boiling of water removes dissolved oxygen. This is a very common experiment done for rusting. It's also a very common experiment done for respiration and photosynthesis. So for the pure bio students, this is another thing you can learn. When you boil water in a setup, it is to remove any dissolved gases, including oxygen. Now, after boiling the water, you must place a layer of oil on top of it. So it's both. You need to do both. Boil the water and place a layer of oil, and this prevents oxygen from dissolving. Next, how would you remove water from a setup? Now, this we have learned in chapter 1. To remove water from a setup, you can use a drying agent. The most common drying agent we use is just anhydrous calcium chloride. Okay, so anhydrous calcium chloride is a drying agent that helps to remove water from the setup. Okay, so shown here we have 4 different test tubes, test tube A, B, C, D. Okay, now there is actually a table on the next page, all right, that you need to fill up now. But before we get there, I would like us to take a close look at A, B, C, D, each of them. Let's think through what is not present. In A, is it oxygen that's not present or is water not present? How about in B? How about in C? How about in D? All right. So have a think through which condition is present, which condition is not present for rusting. Now you can look at the procedure. Now to investigate this, to do this experiment, basically you clean 8 iron nails, can be 10 iron nails, can be 5 iron nails, doesn't matter. It's a reasonable number. So clean the iron nails with sandpaper first to remove any rust that's already present. Now you must measure the initial mass of the iron nails. Place the iron nails into the 4 tubes ABCD and measure the final mass. Now, note the change in mass. What is this change in mass? There should be an increase in mass if rusting happens. Why? Why should the mass of the nail increase? If you look at rusting, you are literally going from iron metal to iron 3 oxide. The solid goes from Fe to Fe2O3. This should have a larger mass. So rust should have a larger mass than the iron nail. So if rusting has occurred, there should be an increase in mass. All right. So the variable that we are measuring for rusting is always the increase in mass. So now let's look at the 4 tubes. A, B, C, D. Please feel free to refer to your notes as we go through. Now A has boiled distilled water with a layer of oil. So boiling of water, layer of oil, this tells you that oxygen is absent. There's no oxygen, but water is present, of course. But even though water is present, there's no oxygen, therefore, there's no rusting. There's no change in the mass of the nails. Test tube B. Test tube B had a drying agent called anhydrous calcium chloride. So test tube B does not have water. Water is absent from B. But oxygen, of course, is still present in the air. But even though oxygen is present, because you don't have any water, there will be no rusting. There's no change in the mass. And then come to C and D. Now, C, you might be tricked easily in C because C says boiled distilled water, right? You might think that C has boiled water, therefore there's no oxygen. But remember, to get rid of oxygen, you must do 2 things. Boil the water and put a layer of oil on top. Both must be done. In C, there's no oil. You just boil the water, meaning the oxygen in the air can dissolve back into the water. So, in C, oxygen is still present. Water is also present. So, there's rusting. If there's rusting, the mass of the nails will increase. And finally, in D, both oxygen and water are present. But beyond that, salt is also present because you have sodium chloride in D. Salt is also present. Hence, there's a lot of rusting. So, what is the effect of salt on the speed of rusting? Salt, or really the presence of ions, increases the speed of rusting. Because in test tube D, you can clearly see that just because I added a little bit of sodium chloride into the solution, it actually resulted in a lot of rusting happening. Okay? Now, this is also the reason why iron near the sea rusts quickly. So like your cars, if you park the cars near the sea and the car paint is scratched off for some reason, the car iron will actually start to rust very, very quickly because the presence of salt in the seawater actually increases the speed of rusting for the iron. Okay? Now, next, with reference to changes in oxidation state, deduce whether iron, Fe, is reduced or oxidized during rusting. That was exactly what I asked you just now. So Fe, iron, is oxidized as the oxidation state of iron increases from 0 in Fe to plus 3 in Fe2O3 dot XH2O. Okay? So again, the rust is actually Fe2O3. The XH2O just indicates that it's hydrated iron trioxide. Okay, so that's the link between rusting and redox. So rusting is actually also a redox reaction. So now that you know that Fe is oxidized, may I know what's reduced in rusting? Have a think about it. Which substance is reduced during rusting? Now, finally, rusting is not desirable. Rusting actually makes the iron metal weaker in strength. It actually becomes weaker. It becomes more brittle. The iron will start to flake off. The rust flakes off, so the iron flakes off with it, right? So we want to prevent rusting, or else our iron structures become weak. How do you prevent rusting? The whole idea is just to prevent the iron from coming into contact with oxygen and water. That's the whole idea. If I can prevent the iron from coming into contact with oxygen and water, I succeed in preventing rusting. So how can you do that? Well, simple things. I just need to apply a layer of something that protects the iron from coming into contact with oxygen and water. So what is this layer that I can apply? I can apply a layer of paint. The layer of paint will prevent the iron from coming into contact with oxygen and water. I can apply a layer of oil or grease. I could use a coating of plastic. I could even use a coating of metal by electroplating a metal onto the surface of the iron. All of these work. All right. Okay. Now, besides that, we can also use alloys like stainless steel, and this is what we really want to go through. Now, stainless steel contains chromium. So when you have stainless steel, let's say you have a piece of stainless steel, the chromium metal reacts with oxygen. And when the chromium metal reacts with oxygen, it forms a layer that's impermeable. Impermeable layer of chromium 3 oxide. Chromium 3 oxide is Cr2O3 because the 3 refers to the oxidation state of chromium. The oxidation state of chromium is plus 3, therefore it's called chromium 3 oxide. Now, this is an impermeable layer. Impermeable means what? So the bio students, you have heard partially permeable. Partially permeable means it allows some substances to pass through it. Impermeable means nothing passes through it. Not even water, not even oxygen. So the whole idea is this layer of Cr2O3 is impermeable. Therefore, water and oxygen cannot pass through it. It prevents the iron metal below from coming into contact with oxygen and water. Okay? Now, the great thing about this layer is that even if it's scratched off, the chromium below immediately reacts to form back the oxide layer. So this oxide layer, even if you scratch a little bit off, there is still chromium metal left in the stainless steel, which can react with oxygen rapidly to form back the Cr2O3. So the iron will not rust even if the outer layer is scratched. So this stainless steel is very durable, very long lasting, very resistant to rusting. That's why stainless steel is very good. It's used to make so many things: pots and pans, forks and spoons. Surgical instruments are also made of stainless steel to prevent rusting. Okay? Now, on the other hand, you can clearly see for painting, oiling, plastic, electroplating, the major disadvantage is that once the layer of paint is scratched off, or once the layer of tin is scratched off, the iron will start to rust. You have all encountered this. So in primary school or in lower sec, if you were bored, you started scratching the table's legs. If the paint is scratched off, your table will start to rust rapidly, actually. I'm not sure if you have noticed, and this is why we always tell you, don't scratch the paint off. Because once the paint is scratched off, the iron will start to rust. Because the iron is exposed to air containing oxygen and water. Okay, so we have covered these methods: painting, oiling, plastic coating, and electroplating, as well as use of alloys. The last method, which is also very important, okay, so you need to know stainless steel very well. Stainless steel is very important, as well as sacrificial protection is the last method. Now, sacrificial protection means I sacrifice another metal to protect iron. So the idea is in sacrificial protection, I attach a more reactive metal to iron so that the more reactive metal will react with oxygen and water instead of iron. So for instance, I can attach magnesium metal to iron. If I attach magnesium metal to iron, what happens is, let's say I put Mg. Mg is more reactive, right? So Mg is more reactive, so it should react with the oxygen and water faster than iron. That makes sense? So by doing so, it ensures that the iron doesn't react, it doesn't rust. Okay? Now, we don't have to use magnesium. You could do the same thing with zinc. Iron, attach a block of zinc. Again, zinc is more reactive than iron, so it will react with oxygen and water faster than iron would. So long as you attach a more reactive metal to iron, this is called sacrificial protection. Now, why is it called sacrificial? Because the more reactive metal will react away with time. So imagine the magnesium block will become smaller and smaller and smaller and smaller and smaller as it reacts away to form magnesium oxide, magnesium hydroxide. All right. So the idea is the magnesium metal will slowly react away. It has sacrificed itself. Magnesium has sacrificed itself to protect iron from rusting. That's why it's called sacrificial protection. So you need to replace the magnesium blocks frequently because the magnesium metal will react away. All right. Now, this idea of sacrificial protection is commonly used in ships. Why in ships? Because the ship is made of steel, which is iron. It could rust. Moreover, the ship is in water. Worse still, the iron will rust even faster in seawater. So it's very important to use sacrificial protection because I can't possibly paint every single corner of the ship. There might be some corners of the ship that are not fully painted. So to prevent rusting, we need to attach a block of magnesium to the iron metal of the ship. The idea is I don't need to fully cover with the magnesium. Even if the magnesium covers just a small bit of the iron, it will be able to protect the iron from rusting. All right? Can? So that is the idea of sacrificial protection. So if I attach a more reactive metal to iron, then I will be able to protect the iron by sacrificing the more reactive metal. But what if the iron metal were to be attached to a less reactive metal, like copper? So copper is less reactive than iron. So what will happen now? Iron will react in place of copper. Why? Because iron is more reactive. So because iron is more reactive than copper, if I attach copper to iron is more reactive, it reacts in place, it will rust even faster, you know. Now it's the opposite, right? Instead of protecting iron will sacrifice itself to protect copper, which of course is not what you want. You want to protect iron. Iron is our construction material. So you must be aware. Sacrificial protection means I attach something more reactive than iron to iron. All right. If I were to do the opposite, I attach something less reactive than iron to iron, the iron will rust even faster. And that's not what you want. Okay? And with this, we have finally come to the end of this chapter on reactivity series. I hope you have enjoyed learning about all sorts of reactions. I hope you have now a greater and deeper perspective of how metals and chemistry impacts our life. So please rewatch all 3 lecture videos in full, pause, reflect to think, revise. All right. And if you have any questions, please feel free to ask. I'll be happy to answer your questions. And I look forward to discussing more with you about metals when I get back to school. Thank you and bye bye.